Okay, so this section is on triple integrals. And so I know it's funny because in Calc 1, you see one integral and you can never imagine that there would be three of them stacked side by side, but there can be, okay? And so you want to recognize when a function of three variables is integrable over a rectangular box. Evaluate a triple integral, expressing it as an iterated integral. Recognize when a function of three variables is integrable over a closed and bounded region. Simplify a calculation by changing the order of integration. And then the last thing is calculate the average value of a function of three variables. Okay. All righty. So the thing about triple integrals is not much different than double integrals volume. So I just want to, I'm going to give you a motivation before we really go into triple integrals. And my motivation is that last problem that we just did. Okay, so here's the motivation. Okay, so from the previous section, we did this problem. Wrong problem. Wrong problem. Okay, so my motivation is this previous problem that we just did. Okay, so I was trying to calculate the volume over top of this particular region. Okay, so as you can see, when I do the volume underneath, if I do the area over a region of a function over top of that region, it gives volume. Okay, so from this previous problem, as you can see, we have the double integral over the region R, and then it was Z top minus Z bottom dA. Okay, I can also write that. So this is the motivation. Whoops. So the double integral, I'm still not finding out why it's not writing yet. There we go. So the double integral over the region of Z top minus Z bottom dA, whether it's dy, dx, let's leave it dA for a moment. Well, you know, if I just integrate the double integral over the region, and then if I do the integral from Z bottom to Z top dz dA, then when I integrate this inside piece, that inside piece right there is just going to give me Z evaluated from Z top to Z bottom. So this piece right here is the same as this piece right here. In other words, I'm saying if we go back to this picture, Z starts at Z bottom and it goes all the way up to Z top. So if I integrate DZ from Z bottom to Z top, that's the same as doing the integral from Z bottom to D top of DZ. So let's start with integrals over a rectangular region. So compute the volume of the region enclosed by Z equal to let's give you Z. Well, okay, let's not do that. Let's use my so a triple integral all right, is the triple integral. And this time it is over a domain, we call it T, of some function f of x, y, z, dz, dy, dx. Okay, so it's the same way you derive the other one. You divide the block up into little pieces and then you shrink the little pieces and they go, the size goes to 0, n goes to infinity. You end up with a triple integral. Okay. So something very easy. Evaluate the triple integral over T of x, y, the sine of yz dv. Okay, so dv is going to be dz, dy, dx. It could be dz, dx, dy. It could be dx, dy, dz. There are like 6 different ways I can do that. Okay. All right. So T is the parallelepiped bounded by x equals pi, y equals pi over 2, and z equals pi over 3 in the first octant. Okay, so I have a rectangular box. It won't let me draw it. It will not let me draw this. It is giving me, okay, thank you. Thank you. It's in the first octant, so it has to stop there. Okay, so there's my box. Okay. All right, so I'm integrating over that. So I'm going to get the integral. So x, so let's do, so if I do x goes from 0 to pi, and then y goes from 0 to pi over 2, and z goes from 0 to pi over 3 of x, y, the sine of yz, dz, dy, dx. Okay. Okay. So that is the integral from 0 to pi, the integral from 0 to pi over 2, and then I'm going to integrate the inside with respect to z. So when I integrate that with respect to z, I'm going to get, well, the x is not going to move, and I have a y. Then I'm going to get minus the cosine of yz, and I'm going to divide by y. Yay, that's nice for me. And then that gets evaluated between 0 and pi over 3. And then I'm going to have dy dx. Okay. So when I do that, I get negative the integral from 0 to pi the integral from 0 to pi over 2. And then the y's are gone. Don't have to worry about them. So I have the cosine of pi over 3 times y. So I get the cosine of pi over 3 times y minus the cosine of 0, which is 1. And that is dy dz. Okay. So now I get the integral from 0 to pi. When I integrate this, when I integrate the negative 1, that's just going to give me y. And when I integrate the negative cosine of pi over 3y, that is going to give me 3 over pi, the sine of pi over 3y, and this will be plus, and that gets evaluated between 0 and pi over 2 dx. Okay, are you following?
Yes.
Okay, so this is the integral from 0 to pi. And so now I'm going to put pi over 2 in for y. So I get pi over 2 plus 3 over pi, the sine, and I threw away my x. Oh, I got an x there. I have an x here. I have an x here. Okay. The sine of pi squared over 6. And then when I put in a 0, I get 0. So this is dx. So that whole thing comes out as pi over 2 plus 3 over pi, the sine of pi squared over 6. Then I'm going to integrate that and get 1/2 x squared, evaluated between 0 and pi. Okay. So that gives me 1/2 pi squared pi over 2 plus 3 over pi, the sine of pi squared over 6, which I have conveniently taken out the 1 over 4 and written it as pi squared over 4. Yeah. So that's going to leave me pi plus 6, the sine. There's the answer. So when you integrate over a rectangle, that's what you get. Okay, so when you integrate over a rectangle, those are the kind of functions that you get integrating over a rectangle. Okay. Recognize when a function of 3 variables is integrable over a closed and bounded region. Simplified calculation between them. Three values. Okay. All right, so let's suppose a region is Z simple. Now we've talked about vertically simple and horizontally simple. Now we want to talk about Z simple. So maybe I have something that looks like this. And then so I'm going to draw something that looks like an oil tanker. Okay, so this thing on the top, so now if I were to look at Z, you can see that Z1 of XY is less than or equal to Z is less than or equal to Z2 of XY. So now the triple integral over T of F of X, Y, Z dV is simply equal to the double integral over the region times the integral from Z1 of XY to Z2 of XY, F of XYZ, and then DZ dA. Okay. So you need to project R into the XY plane. All right. And then you integrate with respect to Y. Or X if horizontally simple. So you have Y1 of X is less than or equal to Y is less than or equal to Y2 of X. Where A is less than or equal to X is less than or equal to B. So therefore your double and your triple integral over T of F of X, Y, Z dv now becomes the integral from a to b, the integral from y1 of x to y2 of x, the integral from z1 of xy to z2 of xy of your function f of xyz dz dy dx. Okay, now if the region is horizontally simple, actually, let me get rid of this. If the region is x simple, then you would get x simple where x1 of y is less than or equal to x is less than or equal to x2 of y, and c is less than or equal to y is less than or equal to d. Then your triple integral over t of f of x, y, z dv will be the integral from c to d, the integral from x1 of y to x2 of y, the integral from z1 of xy to z2 of xy of f of xyz dz. Then you would do dx next, and then you would do dy. Okay. Okay, so use triple integration to find the volume of the tetrahedron bounded by the plane z equal 1 minus x minus y in the first octant. Okay, how would we begin to do this, Anaya? How would I do this?
I don't know. I enjoy watching you do it.
Okay, so z equal to 1 minus x minus y. What kind of surface is that?
You said z equals to what?
Equal to 1 minus x minus y. So if you rewrite that, you get x plus y plus z is equal to 1. What kind of surface is that? You don't know?
Isn't that ellipsoid?
No, it's way simpler than that. So a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. That's a plane. So here, A, B, and C, which are the coefficients, are a, so this is a plane. So it's a plane such that it goes through the point 0, 0, 1, 1, 0, 0, and 0, 1, 0. So this is a plane. And it goes to these points just like this. Okay, so here's the plane. So Z is equal to 1 minus x minus y. So that's the thing on the top. So the thing above ground, this is the point 1, 0, 0. This is the point 0, 1, 0. And this is the point 0, 0, 1. Okay, so the surface on the top happens to be the plane. So the plane is the surface above the x-axis, above the xy plane. So now the question is, what is R? Well, R, remember, you have to project down to the ground. So here's my region R. So that little triangle on the bottom, that's R. So if I draw R, R looks like this. That's R. Okay. So now I have to figure out how to integrate over R. So I want to figure out, how do I integrate over R? So the way I integrate over R is I start off and say, well, this is the point 1, 0, and this is the point 0, 1, and this is the line y is equal to 1 minus x. So now I can clearly see that z goes between 0 and 1 minus x minus y. And I can see that y goes between 0 and 1 minus x, and then x starts over here and goes all the way to 1. So x goes from 0 to 1. So if I do the triple integral, just dv, that will give me volume. Okay, with no function, f of x, y, z is equal to 1. I just get volume. So therefore, I'm going to get the volume. It's going to be the integral from 0 to 1, the integral from 0 to 1 minus x, and the integral from 0 to 1 minus x minus y, dz, dy, dx. So when I do the integral for that, that gives me the integral from 0 to 1, the integral from 0 to 1 minus x, and then I'm just going to get z evaluated from 0 to 1 minus x minus y, dy dx. So that's the integral from 0 to 1, the integral from 0 to 1 minus x. And then I'm just going to get 1 minus x minus y. Dy dx. I think we did this integral. Integral from 0 to 1. I'm going to get y minus xy minus 1/2 y squared. Evaluate between 0 and 1 minus x dx. And I'm pretty sure the answer turns out to be 1/6. Yeah. Okay. All righty, come with questions tomorrow.
Okay, I will.